It is section 6.2, volumes using cylindrical shells. Some volumes may not be easily determined using the previous methods, such as the disk method and the washer method. In this section, we'll introduce another method called the method of cylindrical shells, or simply the shell method. Consider the region bounded by the graph of a function y equal fx and the x-axis over the interval ab as in this figure. Now we choose L left over A, but you can choose L right over B. But here we chose this one. We generate a solid by rotating the region about the vertical line, x is L. Then you can imagine the solid. We'll try to get the volume of the solid. And we'll use the same technique, the limit of Riemann sums. So we begin with partitioning. We partition the interval into n subintervals. For each subinterval, we try to make rectangle so that the collection of rectangles will approximate the whole region. For instance, in the kth subinterval, we can choose a CK, then the approximating triangle has height f at CK, and the width must be delta xk. Now we rotate each rectangle. Then each one will make a cylindrical shell. We try to compute the volume of cylindrical shells and add them to get Riemann sum. Okay, here we have the volume of the shell. The kth one, delta Vk, that is now, okay, let's go back over there. Here, when it is rotated, then now the volume of the shell can be computed in this way. Now, on the bottom is a washer, and now height is multiplied, then we can get the volume. So we have to get shell, the washer area, that is with a large one, pi capital R squared minus pi small r squared. Then now the washer area will be gotten and height is multiplied to get the volume. That is exactly here happening. Pi capital R squared minus pi little r squared and shell height. And with some algebra, we can get here that term. And now CK is the center of the subinterval. So here that is 2 pi, and the distance from L to the midpoint of the subinterval. So it is like 2 pi r, and now that is here the thickness, and that is a height. Okay. Okay, that is the term, and we add them through case 1 to n, then we can reach at this one. Now that is 2 pi and ck minus l, and this height, and that is thickness. Now when you try to get integral, definite integral, the ck will be changed to x, and now delta x will become here dx. So we reach at this one, integral from a to b 2 pi x minus L fx ds. That is playing the role of r. So 2 pi r and fx is height. So this whole thing is the same as the area of the thin shell at x. And now the area is integrated. So the main idea is the same as earlier technique. But if we try to get here now the area of the thin shell. Okay, we summarize the formula. The volume is now integral from a to b, 2 pi shell radius and shell height and dx. So this portion is the same as the area of the thin shell. When we derive the formula, we use the limit of Riemann sums. This technique will be used again to form definite integrals for various applications. Let's go to examples here. The region bounded by the curve y equals square root of x, the x-axis, and the line x is 4 is revolved about the y-axis to generate a solid. We want to find the volume of the solid. Now this cyan colored region is rotated about the y-axis. So you can imagine the solid made by this revolution. Now here we have to get shell area, thin shell area. Now x is moving from 0 to 4. So integral in x direction 0 to 4. And now because it's a center, now once you choose any point x between 0 and 4, then that will be r. So 2 pi r. And now height, the y value is height, so square root of x. So that whole thing is the area of thin shell. So if you finish the computation, evaluate the integral, then that will be the answer. Okay, let's do it. 2 pi can go out, and then from 0 to 4 integral, and x to the 3 over 2 dx. That is same as now 2 pi times, and the antiderivative of that term is same as x to the 5 over 2, and we put over there 2 over 5. Right? And evaluation from 0 to 4. Okay, the coefficients over there is same as 4 pi over 5, and now when x is 4, it will become 32. When x is 0, it is 0. So that this is the final answer. For the problem in the previous example, find the volume using the washer method. Okay, let's do that. Here, I'll use a red pen. And if we want to use washer method, then now we have to get integration in y direction when x equals 4 and here y is 2, so that y is moving from 0 to 2. Oops, here, not that one. That is now 0 to 2 over there. And for each y, and that is now here, line segment will be rotated about the y-axis, making a shell. Now we have to find the area of a shell for that one. So for this one, ay equal, here now capital R is 4, so that pi 4 squared minus pi times, here that one is now, this is x, so that from this curve, x is y squared. Okay, so y squared, squared. So it's y to the 4. So that is same as pi 16 minus y to the 4. Right? Okay, we found ay, and this ay must be integrated from 0 to 2. Okay, let's do it here. So the volume is the same as from 0 to 2 ay, that's pi, and 16 minus y to the 4 dy. So that is same as pi. Okay, and then that is a 32, 16 times 2, and minus. Okay, now here there is now y to the 5 and 1 over 5. Okay, let's write down 1 over 5 first, and y to the 5, and evaluation from 0 to 2 like that. Okay, so that is same as now pi times and 32 minus, that is when y is 2, then it's 32, so that there's a 32 5, and once we put 32 out, then 32 pi times and 1 minus 1 over 5, so that is 4 over 5. So the value and here they are the same. Okay, you can get the same answer. Okay, use the method of cylindrical shells to find the volume of a solid obtained by rotating the region bounded by the curves and about the y-axis. Okay, first you have to understand the problem. Sketch is one way to understand it. Now before that, let's try to manipulate this term a little bit. Okay, that is same as minus x squared minus 5x plus 4. So we have x-axis separation, 1 and 4 separation, minus minus. Okay, so here, and once it is 0, then x is 1 and 4. Then here y must be 0, right? So we have 2 zeros for this curve. Okay, so let's now sketch the graph. Okay, here there is a y-axis, that is now x-axis. Now 1 and 4, and that is open down, so it is coming up that way. Okay, coming up that way and go down like that. There's 1, this is 4. And y equals 0 is x-axis, so that region, that is the region, and that is rotated about y-axis. Okay, so that it is rotated about y-axis, and now we'll use the shell method, so that now once it is rotated, then shell will be found if a vertical line segment, that one is rotated, then it will make a shell. So that means that we have to integrate from 1 to 4 in x direction, and the area, shell area, must be computed. Okay, we can compute it. Now, is rotation, the axis of is this one, so that here, this is r for each x here, so that ax, area of the shell, is given 2 pi x, 2 pi r, and height. Height is, we know that is the height, right? So that is now minus x squared plus 5x minus 4. So from this one, the volume must be same as from 1 to 4 integration, and 2 pi x and minus x squared plus 5x minus 4 and dx. I guess from now on, you can finish it quite easily. Do it yourself, okay? Okay, now we'll use the shell method to find the volume of the solid obtained by rotating the region bounded by the given curves about y-axis. Okay, so rotation is about y-axis. Okay, let's try to make show the region to understand the problem better. This is y-axis, that is x-axis, and now this one is when x is 4, the value is 0. When x is 0, then the value is 4. So that looks like that. That is 4 here. That is 4 here. And this region is rotated about y-axis. And of course, now y equals 0, x equals 0 is used. That is x equals 0. This is y equals 0. Okay, now it's rotated. We'll use shell technique, which means that once it is rotated in that direction, then each line segment will make a shell. Okay, that means we'll integrate the shell area in x direction, moving from 0 to 4 for each x. Now, let's try to get area of the thin shell ax, that is same as now 2 pi r, which is x. Now the height, what is height? That was twice of square root of 4 minus x, right? So from this one, the volume is the same as integral from 0 to 4. And now, okay, we have 2 pi, so that, okay, we have a 4 pi and x and square root of 4 minus x dx. Okay, so for that one, let's try to put 4 pi out of the integral and x and square root of 4 minus x dx. Okay, for this problem, we may introduce u for 4 minus x, change of variable, or u substitution. U is now 4 minus x, then du equal that derivative is minus 1, and so that minus dx. Okay. Now here also we need that one, so that we know that x is, moving this on the other side, and u the other side, so that 4 minus u. Now, once x equals 0, then u is 4. Now x equals 4, then u equals 0. So the given integral volume, that is same as 4 pi, and here 4 and 0. Now we are making u integration, so that for the corresponding value for u must be bottom, because 0 is on the bottom. And now 4 is upper bound. Now the corresponding value of u must be the upper bound. Okay. Now x is 4 minus u, and that one is 4 minus x u, so that is u half power, and here dx is same as minus du. Right? Okay, for that one, now this minus with that lower and upper bound can be changed, so that is 4 pi integral from 0 to 4, and we can rewrite this one in this way. Now there is a 4 times of u half power minus u to the 3 over 2. Okay, now that's du. Now from now on, it's not too difficult to get the evaluation, so you can do it yourself, so you can get the answer here. Okay, let's go to the next one. use the shell method to find the volume of a solid obtained by rotating the region bounded by given curves about x-axis. Now, rotation is about x-axis. We have to understand the problem better. Again, I'll say a good way is to sketch. Okay. Let's try to make a picture for that. Okay, this one is open left and quadratic parabola, open left. But the value x equals 0 when y equals 0 and 2, so that one is making such a shape like that. Right? Now y equals x is given here that way. There's y equals x, straight line, so that region, okay, I'm sorry, this is a little bit ugly. So let's try to make, okay, try one more time. So that is now coming up here and passing straight line. Okay, so that is the region that is rotated about x-axis. So we are trying to use the shell method so that shell will be made along with that line segment. So our integration must be from 0 to in y direction here, that point. Okay, let's say this is D. So from 0 to D, and for each y, we have to make the area of the thin the shell. Okay, so first we'll try to find that one, how we match two things. Then now 2y minus y squared equal y, so that the same as now y squared. If we move everything to other side, then there's now minus y equals 0, so that now there is 0 and the point is now there is 1. So y is moving from 0 to 1. For each y, we have to get the area within the shell. So ay, that one is the same as. Now, y is the r, so the 2 pi y, and then now the height is from here to there. So that one is this x, and that x must be subtracted. Okay, this one is now y, x is y, that x is now, okay, this x is this one, x is 2y minus y squared. So here, this is a 2y minus y squared, and that is now y, so that minus y, right? So we can rewrite this one, 2 pi y, and that is here y minus y squared, okay? That's area at area of the thin shell at y. So here, the volume must be same as from 0 to 1. Y is moving from 0 to 1, and now 2 pi, and if we multiply y over there, then it's y squared minus y cubed and dy. Okay, 2 pi is here. That's 1/3 of y cubed minus 1/4 of y to the 4. And now we evaluate from 0 to 1. So that is now 2 pi times 1/3 minus 1/4, which is 1/12. Right? So that's the final answer. Okay? Okay, let's try to solve the last problem of the section. Again, we'll use the shell method to find the volume of a solid obtained by rotating the region bounded by the given curves about line y equal 2. Now the axis of rotation is y equal 2. So that along with that line, we are making rotation. Okay. Now already the graph is given, so that one will be rotated. Now here, so in this case, region is moving from 0 to 1. For each y, if we are choosing any y here, then now once it is rotated, then this line segment will make thin shell. So we have to get area of this thin shell, AY, okay, AY. That is now R is, okay, 2 pi and R. Radius is same as from 2 to y here, right? So that's 2 minus y, okay? The radius is 2 minus y, and then now height is now x value here. That x is same as this one, so that is 12, and y squared minus y cubed, right? So that is the area of the thin shell. Now y is moving from 0 to 1, so the volume must be integral from 0 to 1. Now the coefficient is 24 pi, and here 2 minus y, and y squared minus y cubed dy. Let's try to finish the computation. Okay. Now that is 24 pi, okay, equal, that's from 0 to 1. Okay. That is y squared, 2y squared, 2y squared. Okay. Now, and that is 2y cubed minus 2y cubed and y cubed, so that minus 3y cubed. I guess we don't make any mistake. 2y squared and 2y cubed, minus 2qy cubed and minus y cubed, so minus 3y cubed, and here plus y to the 4, right? And dy. So here, that is 24 pi times, and that is 2 over 3 y cubed minus 3 over 4 y to the 4 plus 1 over 5 y to the 5 and 0 to 1. So that is the same as here 24 pi, oops, 4 here, 4 pi, and this is same as 2 over 3 minus 3 over 4 plus 1 over 5. So that is same as 24 pi, and now that is the common bottom can be 60, okay? 60 on the bottom, that is 20 times, so that's 40, right? That is 20, so the 40, now 15, so the minus 45, that is 12, so the plus 12, okay? So that will be 7, so yeah, same as 24 pi, and 60 on the bottom, 60, not 16, okay? 60 on the bottom, and on the top is 7. So that is the same as now, okay, 5, and that is 4 pi, right? That is 5 and 2 pi, right? Divided by 12, then it's 2 pi and times 7. So eventually that is 14 pi over 5. Okay, that's the final answer. Okay, this is the end of the section. Thank you.